Hey class, Adam Ward here. I want to talk to you today about gas transfer theory, and this goes along with lecture 20 in your Chopra textbook. And so we've used this Streeter-Phelps report and this typical sag downstream of a BOD source as motivation. And so what I want to motivate our lecture with today is the word I've circled right here from their figure, reaeration. Or really answering the question, how does oxygen get back into the water? How fast does that happen? How much of it will occur? Because that seems to be the major difference between the bottle, closed bottle, which was the lower exponential decay line, and the actual sag that we observe. And so what we're going to take a look at in this lecture is sort of a first principles view of how is it that we have reaeration occur? How does a gas move across this liquid-gas interface at the surface of a stream or river? And so I want to motivate us here with a small pond, a well-mixed CSTR like we've worked on plenty of times in class. This has an inflow and an outflow, has inflowing BOD, remember we're using capital L to represent BOD, and an inflowing oxygen demand, or oxygen level, excuse me. Outflowing discharge, BOD of the well-mixed system, and oxygen level of the well-mixed system. And we've got now two compounds that interact in this system. So in blue you can see BOD, where we've got both a settling and a decomposition loss. Oxygen is being lost at the same rate that BOD is being decomposed. And we've got this oxygen exchange with the atmosphere that is now providing that reaeration. And so what I've wanted to do then is go through and write out a typical mass balance for both BOD and for oxygen. And so the BOD mass balance should be old hat for us by now. Time rate of change on the left is equal to inflows minus outflows minus settling minus decomposition. And for oxygen, we have a very similar reaction, very similar equation. You can see that decomposition loss coupled to the BOD equation. So oxygen concentrations are a function of BOD. But that last term is what we're going to work on today. We're going to try to understand where is it that we can get this reaeration rate coefficient from, and that's related to the current amount of oxygen, O, the saturated concentration in the water, O sat, which we discussed last lecture, and which you would have read about in lecture 20 in your textbook, and this reaeration rate, Ka. So, where does this Ka come from? We're going to start with the idea of a two-film theory. And this dates back to the early 20th century, I think about 19 teens and 20s. And the idea here is that we really have a system that's composed of four layers. At the top of the system, we've got the turbulent, well-mixed atmosphere. And then we've got some shallow film between that well-mixed atmosphere and the water surface itself. And I've labeled that the laminar boundary layer of the atmosphere. And so that's where mixing due to turbulence is not so prevalent, and we expect that we can generate actually a gradient, in this case a gradient in the partial pressures from the boundary layer and from the interface. Now right at the water surface, the partial pressure of a gas in the atmosphere gets converted to a possible concentration of that gas in the water. And that partitioning is due to Henry's law, which we've previously discussed in class. So right at the water surface, we've got some interface concentration, and then that interface concentration has a gradient out to the concentration of the well-mixed turbulent water. And I've labeled those with Ci and Cl. So let's talk about how this could work. Through that laminar layer of the atmosphere, we could describe the flux in terms of a mass transfer velocity, and then we've got an ideal gas constant, the temperature of the air, and those two partial pressures which set up a gradient that drives the flux. Right? So flux is going to be proportional to that concentration gradient through the laminar boundary layer. Very similar in the laminar layer at the top of the water column, we've got a mass transfer velocity KL, and we've got that difference in concentrations that's driving a flux. In between those two, you'll remember from our past discussion, Henry's law is basically our converter from partial pressures in gaseous phase to concentrations in the dissolved phase in liquids. So do we need to know all of those pieces? Actually, what we really want to do is combine these all together. And so through this series of 2 laminar layers, we can add together the rate at which mass will move across that boundary, and we combine those to form an equation that looks something like this. So the net transfer velocity, or v sub v in this case, is equal to the sum of basically the inverse of those previous 2 terms. Right? So 1 over the mass transfer velocity for the liquid, KL, plus gas constant times temperature over Henry's constant times the mass transfer velocity for the gas. And you can rearrange those to solve straight away for that net transfer velocity. Okay, so net transfer velocity, that lets us treat movement of gas across the surface the same way we've done velocities before. We've got plenty of equations to let us deal with velocities both in terms of an effective velocity across an area, or we can convert those into effective Ks and treat them as a first order reaction rate. So two-film theory, most commonly used for slow-moving waters, so think lakes and estuaries in particular, where those laminar boundary layers and those gradients really do set up a limitation on what can happen. In faster-moving waters, such as more turbulent rivers and streams, there's a second proposed equation that we can use, or a second proposed model, called the surface renewal model. And the idea of a surface renewal model is that exchange can really only occur while a parcel of water is actually at the atmosphere, or at the boundary. So you can picture that shaded black parcel of water being subject to turbulent mixing in the stream channel, and so sometimes it arrives at the surface and it can exchange with the atmosphere, and then it's mixed back down into the water column. And so that exchange flux in red can only occur when you're at the surface. So the description of flux, mathematical description, is on the right-hand side here, where the concentration in the well-mixed liquid and the concentration at the surface boundary are both considered. And then that D sub L is a liquid diffusion coefficient, right? So that's proportional to the mixing that we're having in our water. And what's called the surface renewal rate, this RL, and that has units of 1 over time. And so what we're doing here is saying, well, okay, the flux across that boundary has something to do with concentration differences and how well mixed the water is, particularly that surface renewal rate and diffusion coefficient. And so if you look at that equation in the top right compared to what we had on the previous slide, you can see that we could describe an effective velocity now as equal to the square root of that diffusion coefficient times the renewal rate. Everything I did on this slide was about the liquid film control, but you could imagine inverting that picture and doing the same thing for a parcel of air as it reached the boundary layer and then moved on, reached the boundary layer and then moved on. So we can calculate these effective mixing velocities and use those just like we used on the previous slide to estimate that net transfer velocity. Right? And that's what we're really after here, is what is that net transfer velocity, so that we can apply it as we've done with velocities throughout this lecture, throughout this class. Finally, I want to take that model and simplify it for oxygen in the atmosphere, because this is our motivation for today, getting at renewal rates. So we'd previously described a flux across that boundary as the net transfer velocity times the difference in concentrations. And of course, on the left hand of the parentheses there, that Pg over He, that's the partial pressure of the gas we're interested in the atmosphere, and then we're dividing by that Henry's law constant to effectively make that the liquid equivalent minus the concentration at the boundary layer in the liquid itself. Now, we're going to make a couple of assumptions here as we think about oxygen. One is that we're going to have liquid film control. So we're not going to have gas film control. And this is because oxygen is so massively abundant in the atmosphere, and because its Henry's law coefficient shows us that it's rapid to move across the interface. So we'll assume that net velocity is the mixing velocity for the liquid film. And we're going to assume that that partial pressure in the atmosphere is functionally constant. There's so much oxygen in the atmosphere that any reaeration with a stream, any consumption of oxygen in a stream, is unlikely to change the concentration of oxygen in the Earth's atmosphere. So when we make those couple of substitutions, we get that the flux is equal to that mixing velocity, that KL, or that net transfer velocity being KL, times the difference in concentration between the atmosphere, or saturated water equivalent, and what you actually have. Okay, final step, we're going to pull together everything that we've learned in lecture so far. If we picture a CSTR, and the only thing happening is that flux exchanging across the surface of it, you can see on the right-hand side I've written out that flux, K sub L, times saturated oxygen concentration minus actual oxygen concentration multiplied by the area. If we recognize that area is equal to volume of our CSTR divided by its depth, we can rearrange this equation to look like this. So all I've done is substitute V over H and rearrange. And finally, we can express this with a lowercase k sub a. And that's a first-order rate coefficient that describes reaeration. So Ka is our reaeration coefficient. And you'll notice in red there, it's formally defined as that velocity from the liquid film control, KL, divided by depth. Well, that should look very similar to you when we did settling velocities, for example. We had the equivalent K expressed as the settling velocity over the average depth. Right, so we're really just taking things that we've previously known and customizing them to be about oxygen in this case. Okay, so the net takeaway from this lecture is that reaeration coefficient, Ka, or the effective reaeration in your system more generally, is going to have something to do with how far you are from saturation. Right? So the larger that concentration difference is, the faster reaeration will occur. It's a diffusive process, so that should make sense. It's going to be inversely proportional to depth, so shallower systems will have faster reaeration. And it's going to be somehow related to mixing, as described in that KL term. All right, so at this point, what should you know? You should recognize that there are two ways to conceptualize the reaeration of gases into liquid phase. One of those is the two-film theory. One of those is the surface renewal theory. Either way, they both boil down to the fact that we're trying to ultimately get a Ka, or a reaeration coefficient, so that we can describe the net flux of gases across that interface. As a final point here, you'll notice that that term, oxygen saturation minus oxygen level, it doesn't have any caveats on it. So in fact, if you get a system that is super saturated in oxygen, you can bubble oxygen back off into the atmosphere as well. Same mathematics apply, same rules apply, because of course those rules are based in fundamental physics, not an empirical fit to any of these problems. Okay, so I hope this helps you understand some of the derivation that Chopra goes through as we look at two-film theory, as we look at surface renewal theory. And in class, we'll talk about estimates for that reaeration coefficient and how those can be combined with our models for oxygen and BOD to ultimately build that Streeter-Phelps model. Thanks, everybody, and see you in lecture. Bye.